Hello, in this video I'm going to have a brief look at operator overloading and show you how you can use it to simplify your programs. Now, in many of my videos about graphics and physics, the first thing I usually do is create some sort of structure that represents a 2D point, so in this case vector floating point 2D. And I would give it two member variables, float x, and I'll initialize it, and float y, and I'll initialize that too. And somewhere in my main program I'll create some of these vectors. So let's take vector A here and I'll initialize that to 1.0 and 2.5, for example. And rarely I work with just one vector, we may have a bunch of them, so I'll create A, B and C. And when I want to operate on these vectors, I would do it on a component by component basis, so a.x equals b.x plus c.x, and whatever you do for x, you typically want to do for y. So in this case I'm adding the two vectors together. I could also do it using initializer lists. I could say a equals b.x plus c.x, comma, b.y plus c.y. And that would be equally valid. And so far my programs have been simple enough that this is a completely fine way to do things. However, with working on the top-down city-based car crime game, I'm doing a lot of things using physics and 2D vectors. And after a while, it gets a little cumbersome to keep splitting up the code into two lines. And I also mentioned in my Code It Yourself 3D Engine series that one day I'll do a video about operator overloading to simplify the nature of a vector type. And so here it is. And what do I mean by simplify? Well, surely it would be much more convenient to just write A equals B plus C. And the system knows how to go and add them. You can see it gives you a little red wiggly here because it doesn't know how to add these two types at the moment. So let's make a basic 2D vector type that to all intents and purposes can be treated like any other basic primitive in the program. Firstly, the only two members I want my type to contain are the x and y variables. And I want everything within this type to remain public, so I'm just going to keep it as a struct. Let's add a simple constructor to start with. And I'm going to use member initialization syntax. I don't really need a body for my constructor, but I've got to include the brackets anyway. I've got a constructor for initializing the struct, but let's also add a default constructor. And I'll do exactly the same, except this time I'm going to pass in the values 0 and 0. Again, an empty body. And simply because I want to show various interesting things in this video, I'm also going to add a copy constructor, which takes a reference to an object of the same type and constructs with it. Again, an empty body. Since we're creating a vector type, it may also be useful to include some utility functions normally associated with vectors. For example, getting the magnitude or the length of a vector, which is simply the hypotenuse. I never know why Visual Studio doesn't put spaces there. Another common thing to do with vectors is to normalize them. So I'll create a function called norm, which returns a new vector, which is the normalized form of this vector. It becomes the unit vector. So I firstly want to create a temporary variable called r, which is the inverse of the magnitude. And I'm going to construct a new vector where I multiply the components by r. And that will give me the normal. A third useful function may be to get the perpendicular, i.e. something at 90 degrees to this vector. Well, that's easy enough. I'm just going to create a new vector and swizzle the components around. So far we've done nothing out of the ordinary. We've just added utility functions to a struct. But how do we make it behave like a primitive? It's time to start overloading some operators. I think the first operator I'm going to add is going to be simply addition. And to specify that you're overriding an operator, we need to use the operator keyword. And then the symbol that we wish to override. Now I find the syntax of operator overloading a little bit clumsy, but it does make sense once you get used to it. And the intention of this addition is we will take what's on the right hand side and add it to the left hand side. And we'll assume that this particular struct is on the left hand side. And so we'll pass into this operator overload the right hand side, or at least a reference to it. RHS, right hand side. Now we don't want to in any way modify this structure. Simply adding two vectors together shouldn't change either of those vectors. It produces a new vector. So I'm going to return a new object, and I'm going to construct it with a mechanism that facilitates this addition. So I'm going to use the this keyword, which is a pointer to this particular struct. I'm going to take its x parameter, and I'm going to add it to the right hand side's x parameter. And of course, do exactly the same for the y. It goes without saying that the other basic operators are exactly the same. So subtraction, we just need to change the mathematical operator used in the constructor. Multiplication and division don't really make much sense to do a similar pattern. Instead, what we want to do is pass in a floating point scalar. So I'll change this to float. Right hand side can stay the same, but this time we're just multiplying this structure's x and y coordinates by the scalar value. And we'll do exactly the same for divide. So there we have the basic operators. Let's try them out. We can see on this third line the compiler no longer has an issue with it. The red wiggly is gone. But let's see if it actually works. I'll change these values to something different, just so we can follow along. Let's run the debugger to this line. I'll zoom in here and we can clearly see the debugger is quite happy representing our vectors. So I'll just perform the addition, and we can see that the values have changed appropriately. I.e. in this one little operation, we've performed additional code. Note that I'm using the const keyword, and this is used to reinforce the point that the right hand side should not be in any way modified, so if you do try to modify it, the compiler will catch it for you. But what if we wanted to self-modify the vector? So something like a plus equals b. We've got that little red wiggly back. We've not defined what happens for this operation. Let's consider what happened when we did just the regular addition. The addition operator was identified, and so we performed the calculation. So we had .x and .x, .y plus .y, and we created a new object using that result. Let's just call that d. We then returned d, which was copied into the location of a. However, this time we want to directly change the values of a based on whatever's going on the right hand side. We effectively want x plus equals b dot x and y plus equals b dot y. Note that this time we're not copying anything over to a. However, we do want to return something, just in case the result of all of this is used in some other equation. For example, c minus all of that. So when the operator insists that we're going to modify the structure itself, we don't really want to move things around if we can help it. So we're going to work with references. Operator keyword, plus equals is the operator we're overriding. The right hand side is the same as the previous addition. And we'll perform the operation manually. But we're going to use the this keyword again just to make sure we know what we're operating on. So this object's x value plus equals the right hand side's .x value. And the same for y. But I want to return a reference to this object just in case it's used by other things. But I don't want to return a pointer to this object, so I'm going to grab the value of it. Now we can see the compiler is quite happy with that syntax. Multiplication and division are similar, but again we can't multiply two vectors sensibly, so I'm going to change it to a scalar value instead. And we'll just do the same for divide. Very nice. So now we've got the facility to do quite complicated operations. And we can see here the compiler has flagged a little error. We put our cursor over it. No operator divide matches these two operands, and it's basically saying I can't divide one vector by another, because that doesn't make any sense. And because a is a vector, and the result of this results in a vector, it's flagging that as an error. So let's just turn this bottom one into something it can work with, which would be a scalar value. Let's take the magnitude of it. and the compiler is quite happy. So we've now got quite a sophisticated operation on a type we've defined ourselves. But we can handle it as humans like normal mathematics. I'm going to add in two more utility functions which are quite useful for vectors. The first is to get the dot product between two vectors. This isn't an operator overload, but it's just really useful. I'm also going to throw in the cross product between the two vectors. Now these are 2D vectors, so cross product doesn't really make a great deal of sense in this regard, other than giving you an indication of something in a hypothetical z-axis. We can see that our simple two-element vector class is now becoming quite a sophisticated thing. Now this is a simple, quick video about operator overloading, and there's one more type of operator overloading that I'd like to show, and it's the array subscript operator. Now, before you all write in with letters of complaint, I'm fully aware what I'm about to show is really bad practice and probably has all sorts of technical problems and issues. The array subscript operator is exactly what you think it is. It's the square brackets after a variable where you'd usually pass in some sort of index. And in the case of my simple struct, if I pass in a 0, I want it to return the x, and if I pass in a 1, I want it to return the y components of the vector. Either way, the array subscript operator overload is going to return a float. In fact, it's going to return a reference to a float. And I'll explain why in a minute. So we'll use the operator keyword, tell it which symbol we want to overload, and in this instance I'm just going to use a simple numeric index. Size t. Of course it needn't be a simple numeric index, it could be anything you want. Now I could check explicitly here, if I equals 0 then return x, if I equals 1 then return y, but where's the fun in that? Instead what I'm going to do is, knowing that my struct is a simple plain old data type with just two members, x and y, so in memory it will just be those two floating point values. If I take the this pointer, because I know that that's where the start of my struct resides in memory, and I cast that pointer to a floating point number, assuming of course that the x is the first element in the memory of this structure, then I can use some simple pointer arithmetic to access the right value. Of course right now this is all a pointer, so I want to actually return the value. And if you're not well up on your pointers, do check out my What Are Pointers video. Now, it was important that we return the reference, simply because if we didn't have the reference we wouldn't be able to write anything to the array. Because the reference is the data at that location, and we want to change that by writing to it. In this case we're writing an 8 to it. If we didn't make that a reference, you see we can't compile it. It won't allow us to write to that location. But we can happily read from it. There's a lot to our simple type now, so let me just take a minute to tidy up the code. Very nice, a completely custom data type. Now I'm fairly sure one or two of you will have the following concern. But Jared, a 32-bit floating point number is completely insufficient for my calculations. I need a full 64 bits of numerical precision, as described in the specification laid out in IEEE 754 ratified in 2008. Well, don't worry, whilst that's incredibly nerdy, it is a completely valid point. Here we are entirely restricted to single precision floating point numbers. What do we do if we do want fundamentally a different type? Well, one obvious answer is to copy and paste the whole thing and change anywhere where we have a float to the type that you need. But this isn't a very elegant way to do things, and C++ in fact provides us with a tool to do just this: templates. And I'm only going to very briefly skirt around the topic of templates here. Templates can get very complicated very quickly, and I'm just going to show a very simple use case for them. Now the way I'm about to use templates is effectively just fancy cut and paste for the compiler. Using the template keyword, I can specify a particular variable t, and it is through this variable t that the user will specify the underlying type used in the class. So anywhere where we've got float, we now want to change that to t. The current name of the struct, vf2d, implies that we're using a 32-bit float, so I'm going to change this to something more generic. And naturally, wherever we were referring to vf2d, now we want to refer to this generic name. So there we go, and yes, I'm fully aware I can change lots of things simultaneously using clever search and replace options, but it's more interesting visually to do it like that, and this is a video after all. So how do I use this template? We can see the compiler is no longer very happy. Well, one option is to use the numeric name and pass along the underlying type that we wish to use. So in this case, this is the same as it was before. These are our floating point types. And we can see it's all very happy. I can change these floats to doubles. And again, just as happy. But fundamentally, the underlying data type of our x and our y and all of the calculations that are performed upon them are happening using a different primitive type. We could even use integers and shorts, but we have to be careful in that case about what things start to mean. For example, normalizing an integer vector probably doesn't make very much sense. Also, this is now a bit of a mouthful every time we want to create an instance of our vector type. So I'm going to create some convenient shorthand types using typedef. One for float, which will go back to our original name, vf2d, and one for double. And we'll call that vd2d. So all of these now can go back to how they were. And so there you have it, a custom vector type that behaves like a primitive because we've used operator overloading to make it more convenient to use, and we can also use it with different fundamental types. It is both useful and pretty. Very much unlike me. In fact, I like this so much I'm going to include it directly into the Pixel Game Engine header file. I'll put the source code for this video in the GitHub and link to it below in the description. If you've enjoyed it, give me a big thumbs up, have a think about subscribing and come and have a chat on the Discord, and until next time, take care.